Please consider following safety rules for the labs. For this prac, we are going to investigate the effect of radiation on temperature measurement. The apparatus we are going to use for this prac, it is going to be a controlling system, as you can see here, which we are going to control heater, and we can read the temperature of the thermocouples attached to different parts. We can also adjust the velocity for the fan to have a forced convection or natural convection. So we have two main parts. First part, controlling system, and the second part is going to be test section, which includes the main tower with a heating section at the top. Okay, this is our controlling system, which is, we call it HT10, which includes the main power. We can turn on the system with this one. Then we can control the voltage using this knob, and this monitor is going to show the voltage for the heater, and this knob is going to we can select what variable we want to show inside this monitor. So currently it's V, so it's going to be voltage. The second one is amp, and we can show the current there. Then we can connect the fan sensor or velocity sensor or anemometer, we call it, to UA, which is the velocity of the air, to this port, and we can rotate this selector to UA, and using this auxiliary control we can change the velocity of the air and read the velocity. Finally, the lower knob, which is start from T1 to T9, we can use this knob to select the thermocouple and show the temperature of that thermocouple with this monitor in front of it. For this case, we are going to have T6, T7, T8, T9, and T10. So the only thermocouple is going to start from T6 till T10, and we're not going to connect anything from T1 to T5. Okay, this figure shows schematically what is happening inside our testing column. As you can see, we have a metal cylinder, and at the bottom of cylinder we have a fan which we can control it, and the anemometer here is going to show the velocity of that fan. Starting from the bottom, we have thermocouple T6 at the bottom, so it is going to show us the temperature of the inlet air, T6. Then we have 3 thermocouples with different bits at the tip. As you can see here, we are going to call them T7, T8, and T9. They are going to have different properties and different size. Their property and size are going to be presented in the prac handout, so go and check those properties. And around those temperature sensors, we have this radiation shield. As you can see, it's labeled radiation shield. This radiation shield can be raised to have radiation or can be lowered. And how we can have that radiation? Around the cylinder we have this heater or heated area, so we are heating that metal cylinder at this area, and our controlling system is going to control the watt and current of this heater, so we can adjust, increase or decrease the amount of heat we are putting here. And because there is no direct contact between T7, T8 and T9 with heater, the way we are going to have heat transfer from heater to those three thermocouples is going to be just through radiation. We can stop that radiation by lowering this shield and blocking the radiation from heater to those thermocouples, or raise radiation shield to have radiation over these thermocouples. So we can play with this radiation shield by raising or lowering and see the effect of radiation on the temperature. So imagine if you want to record temperature of air, as we are recording here, with a thermocouple with, for example, large bead at the tip of the thermocouple, or small bead at the thermocouple. If we had a hot surface around and we had a radiation, what are those numbers are going to be? Are going to be different numbers for these thermocouples, or they are going to be same? If they are different, what are the parameters? Is it going to be emissivity of the beads going to affect the temperature we are reading? What about the size? What about the color or the surface finish of those tips going to affect the temperature we are reading? So for this experiment, we are going to investigate those effects and how radiation can change our final readings using the thermocouples. And finally, T10 is temperature of these heaters. So the hot surface we created by these heater, the temperature of that surface can be read using T10. That's it. So let's go and start the experiment. Okay, now it's our apparatus, which, as you can see, the first part we have controlling system. The white box beside controlling system is for moving the radiation shield, so we can raise or lower the radiation shield. And the last part, the third part, is the apparatus system, which you can see is a vertical metal cylinder with a heating section at the top. That is why you can see there is a heating shield here, because it's a hot surface. So we have insulation around that hot surface to make sure it's safe to use. And this part is our radiation shield cylinder to raise or lower the radiation shield. So let's go back to the different parts and what are the connections we have. As you remember from the schematic picture, we had 3 different thermometer or thermocouples inside the heating section. As you can see, we have 4 cables here for T7, T8 and T9, and one more which you can see is a bit thicker is for T10, which is the temperature of the hot surface. That is a bit thicker because the temperature of the hot surface is much higher, and we need a bit thicker wire. Those wires. Okay, let's see what are the controls I'm going to apply for this experiment. First, I'm going to change the voltage using this knob and this selector. Currently it's voltage, so I can rotate this knob to change the voltage. As you can see, I adjusted the voltage to 12 volt. What is the current? So current is 4.42 amp. So these are the 2 input numbers we can have for the heater. So the heater power is going to be that voltage 12 times the current. So what about the other temperatures from T6 to T10? we have this knob, which as you can see, starting from, if I rotate for T5, it's going to show me 140 something, which is error basically, because we don't have anything connected to T5. So from T6, we can read using this knob, and for example, T6, T7, T8, T9. So I can read those 4 thermocouples using this one. What about T10, which is the temperature of the heater? For temperature of the heater, I'm going to use the upper knob to see what is the value for T10. So by rotating this knob, I can read the temperature of T10. Okay, so for this experiment, I'm going to do 4 different arrangements. First, I'm going to have, by the way, before I forget, I can change the velocity of the fan we have here by this auxiliary control. Let me increase, first rotate this knob to UA, which is the velocity of the air, and change this. And you can see that here the air, the fan rotating, and we have an airflow inside this cylinder. Or I can decrease this velocity and make it 0. So I have 2 different control for the velocity of the air and the position of the shield. So what I'm going to do, I'm going to have 4 different arrangements. Arrangement number 1, shield is going to be lowered, which is the current position, no radiation, and no forced convection. So the velocity for the air is going to be 0. Arrangement number 2 is going to be, we are going to have forced convection, but still no radiation. So radiation shield is going to be lower. Arrangement number 3, no flow, so flow velocity is going to be 0, but I'm going to raise radiation shield. And arrangement number 4, we are going to have both radiation and force flow. Basically, we are going to have some velocity, plus the radiation is going to be raised and open. We are going to have open surface between the heated surface and thermocouples, so we have radiation there. Okay, let's start with test 1, which is going to be no flow and no radiation. So let's check the radiation shield. It's lowered, and we can check this the shield control. As you can see, shield is down and it's here. So shield is down, so we don't have any radiation. What about the velocity? Yes, it is 0. I can check the velocity with this selector, and as you can see, it's 0.1, 0.2, and it is because of natural convection happening there. So we don't have any forced convection there. So we adjusted all the settings for test 1, and we are going to wait to reach a steady state and read all the temperature T6, T7, T8, T9, and T10. T6 to T9 using this knob, T10 using this knob. Currently it's 113 degree, and I'm going to pause and wait to reach a steady state and come back. Okay, 20 minutes passed. Let's read the temperatures. If for 1 minute the temperature didn't change, you can consider as a steady state. So let's read first T10. As you can see, it's 130 degree. Then let's go and start from T9. T9 is 32.8, T8 31.8, T7 is 31 point, maybe 32.5, T6 is 22.1. Okay, this is for test 1. Now I'm going to start test 2, which is we are going to have still no radiation, so our shield is going to still be lowered, so no touching for radiation shield, but I'm going to apply some force convection by increasing the velocity of the fan. So let me rotate this to UA, which is the velocity of the air, and by controlling or rotating this auxiliary control, I'm going to read the velocity here. Currently it's almost 0, so let's increase and put it 4 meters per second. You can see the unit here, 4 meters per second. So if you listen to the fan noise, you can see the noise of the fan is clear. It's a bit difficult to adjust. Okay, great. So the test number 2, no radiation, but we have force convection. Again, I'm going to wait to reach a steady state and come back and read these temperatures. Okay, 20 minutes passed, we reached almost steady state. Let's read the temperature. So T10 86 degree. Let's do read for T9 24.5, T8 24.3, T7 24, T6 22.1. So this is our test 2, which we had force convection but no radiation. Now I'm going to have no convection but radiation. So to stop force convection, I'm going to make this velocity 0 by rotating this auxiliary control. And to have a radiation, we need to raise this radiation shield. How I'm going to do it? I'm going to push this button. As you can see, it says shield up. Let's push this button. As you can see, this jack raised our radiation shield inside the cover, and we are going to have radiation over our thermocouples and no force convection. To check that, we can check the velocity. As you can see, it's almost 0, so no velocity. Now again, for this case, which is having radiation but no force convection, we are going to wait to reach a steady state and read all those temperatures. Let me pause. Okay, 20 minutes passed and we almost have steady temperature. Let's read the temperature for case 3, which we have no flow but we have radiation effect. So T10 is going to be 122. Let's read the rest. T6 is 22.8. T7 27.2, T8 30.6, and T9 is 28. Okay, so this is case number 3 or test number 3. Now we are going to have test number 4, which is the most important test, and for this test we are going to have both convection, force convection, and radiation. So we are going to keep the radiation shield up, so we have radiation effect on the thermocouples, and I'm going to have some flow similar to the previous case, which was the case number 2, which we had 4 meters per second. Let me increase the a little bit more. So okay, now we have 4 meters per second flow inside our cylinder, radiation shield is up, so we have both radiation and forced convection happening inside the cylinder and for the our thermocouples inside the heating section. So let's wait again and reach steady state and read the temperature for this case. Okay, 20 minutes passed and we almost reached steady state. Let's read the temperature. T10 is 90 degree. Let's go for T9, 24 degree. T8, 24.6. T7, 23.7. and T6, 22.2. So this is our case 4, which is we have forced convection and radiation. For this case, we can write equation for the energy balance for the thermocouple bits. Why and how? Because we have both radiation and convection happening over the surface of the thermocouples, and we can evaluate the temperature of the thermocouples showing us. So let's see the details. Okay, let's see what we have here. We have this bit or tip of thermocouple inside the heated section, which we know what is the temperature of the heated section, which we can read using T10 thermocouple. If our bit is sphere, and for the case number 4, we had both forced convection and radiation happening to this bit. We can write energy balance when we have a forced convection and radiation. Basically, we say whatever heat we are absorbing from the radiation may last using forced convection. You may say, what about natural convection? We can say because we have forced convection and velocity high, we may neglect natural convection. So we can write the formula for convection, which H times delta T. Tm is the medium temperature. Th is temperature of the thermocouple. Must be equal the radiation, the heat absorbed from radiation. Again, T is T for the thermocouple. T surface surrounding is basically the temperature of the hot surfaces, which is going to be T10. Okay, so this is just happening for case number 4. Let's see which parameters we have for this formula. We are looking for Tm, or the medium temperature, or the temperature of the air around this thermocouple, that is why we put that thermocouple there. We have the temperature we are reading using the thermocouple, so this is available. This is emissivity. It is available in your flag handout. Stephen Boltzmann constant, it's available. Temperature of the thermocouple available. Surface temperature, which is T10, is available. The only unknown is Tm, which we want to get, and we don't know H. So if you rearrange this formula, the formula is going to be like this: Tm equal you divide this part with H, so that part divided by H plus something. So if you want to get Tm and you don't have H, it's going to be difficult. So to do that, you are going to draw a graph. X is going to be your H and Y is going to be your medium temperature. And gradually increase H and get Tm. For example, you put 10, 1, 2, 3, 4, 5 in Excel file and get this type of graph. As you can see, after some point, the H is going to reach to the point which by increasing H, you're not going to have that much change for Tm. So at that point, you need to select a point for H and the corresponding Tm. How? You are going to say, for example, if the change of the Tm for this point and the point after that is less than, for example, 1%, I'm going to select this point as a final point and read the Tm temperature, which is the medium temperature. For example, it is going to be 200 watt per meter square Kelvin for H, and the corresponding is going Tm temperature is going to be 23, for example, degree, and you're going to record this value, and then compare this value with the TH from the thermocouples and discuss why they are different, and show me what is the effect of different thermocouples. And you need to repeat this for 3 different thermocouples we have here. We have T7, T8 and T9, which shows we have 3 thermocouples inside, and you're supposed to do this process for those 3 thermocouples and compare those thermocouples and the result we are getting from those thermocouples.